So the problem is to solve or determine the inverse Laplace transform of the function s minus 1 over 2s squared plus 8s plus 11. So the question is very simple if you are able to do completing the squares of the denominator so that you can get a standard expression similar to the standard transforms, and then be able to pick the correct form of the inverse transform. So let's see what you're supposed to do. Now, our question is determine the inverse Laplace transform of s minus 1 over s2s squared plus 8s plus 11. So first, write the denominator in standard form, i.e. complete the square. So this is what we mean. So we'll have 2s squared plus 8s plus 11. I can write this one as 2 into s squared plus 4s and then plus 5.5. And then I'll now complete the square for this expression. Now, b is 4, so this will be 2 into s squared plus 4s. B over 2 squared will have 4 over 2 squared, and then plus. So 4 over 2 squared is 4, and then the original constant was 5.5. So then I mean I need to now add 1.5 so that I don't change the value of the original expression. So this is the same as s plus 2 squared and then plus 1.5, which can be written as square root of 1.5 and then squared. My interest is just to have the expression of the form s plus a squared plus b squared. That's why I'm writing 1.5 as square root of 1.5 squared. Now, so therefore now the expression in the question, s minus 1 over 2s squared plus 8s plus 11 is the same as now s minus 1 over 2 into s plus 2 squared plus root 1.5 squared which can be written as a half, and then s minus 1 s plus 2 squared plus square root of 1.5 squared. Now, when we see this structure of the denominator, then it tells us that probably we are dealing with expressions of this form or expressions of this form. This is because we have an S value and a constant in the numerator. So we are going now to, because already now this one tells us that our A is 2 and our B is root 1.5. So we force S plus 2 in the numerator. And then after forcing S plus 2 in the numerator, we balance it so that the final numerator remains to be S minus 1. So if I write S minus 1, S plus 2 as, so I'm saying that I need S plus 2 so that I can use the standard transform for expressions of this kind. S plus 2 squared plus root 1.5 squared. Now, when I put S plus 2 here, to get my negative 1, then I have to subtract 3 so that this equality makes sense. And once I've done that, then I'll write this one as S plus 2 over S plus 2 squared plus square root of 1.5 squared, and then minus 3 over S plus 2 squared plus square root of 1.5 squared. At least now this one has a standard transform that I can easily provide. But then the structure of the denominator here dictates that the B should be square root of 1.5. So then I'm also going now to force a square root of 1.5 in the numerator here, but then balance it so that I still have my value of 3. So next will be the same as S plus 2, S plus 2 squared, and then plus square root of 1.5 squared, and then minus, so I force a root 1.5, and then S plus 2 squared plus root 1.5 squared, so that I have my original 3. I have to multiply this one by 3 over square root of 1.5. So then now my solution will be the inverse transform of S minus 1 over S2S squared plus 8S plus 11 will now be, remember, we had a factor of a half before we got this expression here. So because we have reduced this expression into standard forms, then we're just going to multiply each of those standard forms by this factor half. So we'll have the inverse transform of a half times this value. So put here half S plus 2 over S plus 2 squared plus root 1.5 squared, and then minus, I'll have 3 over 2 because of that half that was multiplying everything here, root 1.5 inverse transform of square root of 1.5 over S plus 2 squared plus square root of 1.5 squared. Now remember that the inverse transform of S plus A over s plus a squared plus b squared is given by e raised power negative a t cosine of bt, and the inverse transform of b over s plus a squared plus b squared is given by e raised power minus at sine of bt. So our value of b in this of these expressions, b is root 1.5 and our a is 2. So therefore, for this first part here, we'll have e raised power negative 2t and then cosine of root 1.5 t. And then here we'll have e raised power minus 2t sine of root 1.5 t. So therefore, the inverse of the expression s minus 1, 2s squared plus 8s plus 11 will be given by a half e raised power negative 2t cosine of square root of 1.5 t minus 3 over 2 root 1.5 e raised power negative 2t sine of root 1.5 t. If you like, you can factor out the a half and write it as a half into e raised power negative 2t cosine of square root of 1.5 t minus 3 over root 1.5 e raised power negative 2t sine of square root of 1.5 t. You can as well simplify further at this point. You see 3 over root 1.5 is the same as, so if you do this, you'll get 3 divided by 1.5, you'll get 2. So which you can as well write as e raised power minus 2t over 2 into cosine of root 1.5 t minus twice root 1.5 cosine sine of root 1.5 t. Or you could have just left your solution at this point. It is still accepted at this point here. So that is how we get the inverse transform of that given function. So the key thing was to decompose or rewrite the denominator in standard form using completing the square method and play with the expression you have so that it conforms to the standard Laplace transforms which are known, and you get the answer. Thank you.